Welcome to the webinar on demystifying large language models. This is your host Anas. Large language models, or LLM for short, and generative AI, or GenAI, is a hot topic in today's world. Let's understand. What is the first thing which comes to your mind when I talk about LLM or GenAI? The picture on the right, correct? ChatGPT. But is there more to that? We'll unpack it today. Let's start. First thing first, let's unpack some jargons over here or some terminologies. Artificial intelligence is a bigger umbrella term which represents any machine which is capable of reasoning or intelligence, basic intelligence. Machine learning is a subfield within artificial intelligence. Let's understand it this way. Your office Xerox machine can be categorized as an artificially intelligent machine because it prompts you or it guides you that the paper is stuck in tray 2. But can that be categorized as a machine learning? No. The difference between these two is machine learning has to be a system which can learn on its own from the data. It doesn't need to be specifically programmed. Okay, I hope that difference is clear. Deep learning is a further subfield of machine learning which deals with neural networks. So friends, if you have heard about neural networks, that's great. Otherwise, we'll talk that also in a minute. Within deep neural network or DL or deep learning, there are two subfields which are overlapping as shown in the picture: generative AI and large language models. What is generative AI and large language models? First, understand large language models. The large language models, language as in human readable or human spoken language like Hindi, English, French, German, Japanese, and all those. Generative AI is a subfield of deep learning which deals with generating new samples from the distribution. Now, if these words do not make sense, don't worry, we'll just go over that in a minute. For now, let's take a small simple example. Let's, for a moment, believe that you are a good chef and you are experienced in baking cakes. You have noted down all your cake recipes in a recipe book. Okay, so you have vanilla cake, mango cake, cherry cake, pineapple, and blah blah, and other things, right? Now, some customer has come to you and he has asked you to bake a cake which is vanilla pineapple, a very strange combination, but vanilla pineapple cake. Now, you looked into your recipe book and you couldn't find that. There is no vanilla, there is a vanilla cake, there is a pineapple cake, but there is no vanilla pineapple cake. What would you do? Can you mix these two? Of course you can, you are an experienced chef. You can do that, you are an experienced baker. Now, think it like this. This recipe book is your model training, right? Is your model. Does that model has been trained on specifically a pineapple vanilla cake? No. But you can create a pineapple vanilla cake. You can create a new sample. You can generate a new sample from the distribution, which is nothing but the recipe book, right? I hope that is making little sense. Even if it is that doesn't, don't worry. LLMs, on the other hand, is dealing with large language models or natural language, NLP for short, right? This is also a field of generative AI, but generative AI is a much larger field which deals with multimodalities. By multimodalities, I'm saying that generative AI can be done not only for text or human languages, but it can also be utilized to generate pictures, videos, speech, other unstructured data. Okay, let's understand a little bit more. This is a picture of a cute little girl. Would you agree? Okay. The only problem with this picture is that this girl never existed. This is totally generated by an artificially intelligent or a generative AI application. Okay. Now, how did this, try to understand what I meant when I just referred to distribution, like picking the sample from the distribution. Now, this model has been trained on tons of images of cute little girls of Caucasian race and with black hair and brown eyes, fair skin. Okay. Now, when it was trained, it has a brief idea about how a girl looks, right? And when we are randomly sampling from that distribution, from that whole knowledge of white little girl pictures, it is generating one. What is it doing? It is taking nose from somebody, it is taking eyes from somebody, it is taking hair from somebody, ears from somebody, and generating it in so coherent way that it looks very, very possible that such a girl would have existed. Similar is the case with LLMs also, what we are doing. What I have been showing you for images is entirely what is being done for the large language models also. And we'll unpack that in a minute. This is just a 10,000 feet view for that. What was there before ChatGPT? There is a field of deep learning which is called natural language processing. It was doing its job well, but let's take a look at the state of that. So we were doing some sort of spam filter, right? We all have known about a spam filter. So we know that, okay, there are these type of words like lottery and jackpot and free and drugs and all those things. If these kind of words occur for a larger frequency, it's a spam email, right? We're also doing sentiment analysis sort of things, like if the movie reviews, is it good or bad, right? How can we automatically categorize a particular review or a Twitter feed? We were doing that sort of, but NLP was lacking seriously in generating coherent text. By coherent means meaningful text or the large meaningful text. It was not able to retain the context that what was said in the last line and retain the context over here in the next line also, right? So if you, before 2022, if you asked any NLP system to generate an essay, it was a Herculean, a very big task for any NLP system. I'm sure that it would not have done. But with ChatGPT, it became very simple, right? So what changed? And now, if you see over here with ChatGPT, this is a screenshot which I've taken 2 days back. If you see over here, I asked it to write a Shakespearean style, like in the way Shakespeare used to write a poem about Elon Musk. I said specifically to it that it should not be 8 line long, more than 8 lines, and it should be funny. I've highlighted few of the points or few of the words over here. Now pay attention to those words. If you know about Elon Musk and Shakespeare, this will make sense. First thing first, the poem is just 8 lines, right? Not more than 8 lines. So it understood what 8 lines long means, not more than 8 lines long means. Also pay attention, the wealth, Tesla, Twitter, Mars, brain, tweet. These are the words which it has picked. So it knows who Elon Musk is. He's a SpaceX, Neuralink. The brain is the part of the Neuralink company which he heads. Twitter he owns, Tesla he owns, and he's a very wealthy person, right? So it knows it has the world knowledge, right? And it can generate coherent text, right? Which is meaningful text, right? This was not possible in the NLP era, vanilla NLP era, as I called it, right? This is only possible with large language models. So does it mean that ChatGPT really understands languages? The answer is yes and no. Okay. Why yes and no? Because it doesn't understand languages as we humans do, but by the fact that it is able to generate, it has some history, some knowledge, some sense of how English has been written, right? So it has some knowledge, not just human-like knowledge, okay, if that makes sense. If that doesn't make sense, we'll just see what LLMs are all about. Okay, so what is LLM? Okay, let's break it down in such a way that first we'll learn that how can we use LLM and what are the different mechanisms in which, and then we'll see that what LLMs are built of. Okay, so the first thing first, you can go to Hugging Face. It's a repository for models. You can download your model from there. Okay, over here the screenshot shows the Meta is Facebook. Facebook has generated a large language model which is Llama 2. It is second version of that. It has 7 billion parameters. What parameters is, what is the models, and all those things will unpack. Just see that how we can download, how we can play around with it. Okay, so this is Hugging Face. It's like a GitHub of models, like how you have GitHub for code. This is GitHub for models. Okay, or you can go directly to the Meta website and download it from there. I have done that precisely. So I downloaded it over here. What I have downloaded on my local Mac computer, I have downloaded a Llama 2 7 billion parameter and the chat version of that, right? If you notice, it just comes with 3 files, not many, just 3 files. One of the file is huge, right? It's around 14 GB or little less than 14 GB worth of data, right? Why? Because we are downloading 7 billion parameters. Each parameter is a float 2 byte number, right? So 7 billion into twice is roughly around 14 GB. Little less than that because Hugging Face would have done some sort of compression over there. When I unpacked this 14 billion file, I thought that there will be some code, right? Like how this LLM works, but no. This is what I got, right? A long sequence of numbers, right? That's it. That's it. So how can a large sequence of numbers, by the way, these are the parameters which we are talking about, 7 billion parameters, that means 7 billion such numbers are there. How can that 7 billion numbers translate into generating a Shakespeare way of writing a poem about Elon Musk? How did that happen? And that's the magic, right? So this 7 billion parameter is actually, we can consider it as a zip file of the internet, right? Why? Let's see. For that, we have to understand that how these Llama 2 models were trained. So they were approximately trained on 10 terabyte worth of text data downloaded from the internet. So how they were downloaded? They were like crawlers, crawl through the internet. They will go to Wikipedia, books, digitized books, Reddit, Quora, all over the internet, blogs, everything, wherever it can find text data, and then it will pump it to what? 6,000 GPU cluster for 12 days. That's the training time. It was worth $2 million few years back, right? And what is the outcome of this? This is 140. 140 means this is 70 billion parameters, right? But in our 7 billion case, it will be 14 GB file. So we got a file. That's why I'm calling it a zip file, because after all this 10 terabyte text of data, when we trained it on a model, all I'm getting is 14 GB worth of file. But somehow that represents, or that brings the essence of what was there present on the internet, how humans write to each other, right? That whole essence is there. Okay. How do we run it? Okay. The running part is the inference part. We were talking, this is the training part, right? So let's not get confused between training and inference. They are two separate things. One is how it was built. The second part is inference, is how we are using it. So when you use ChatGPT through a web interface, you are just using it. You are not training it, right? So how do we use it? There are multiple ways. One way in which I did few years back was that I downloaded that model. Those models have parameters. They have weights and embeddings. Embeddings we'll just deal in a moment. Weights are nothing but the parameters, right? We'll just deal with that also. And few line of Python code. Without any internet, self-contained system on your Windows or Mac with having GPU support, you can run it. Okay. Is that simple? Just running? Yeah, you can run. And actually you can access any open source models. When we say open source, it's technically talking about where the parameters have been released. You can download it from the internet. Those are open source. Closed source are like OpenAI or your Google Gemini. Those are closed source because you cannot download the weights or the parameters for that. But Meta has released, and few other companies have also released their weights. They have trained it and they have released the weights. Those are open source. So that's the difference between open source and closed source. Okay. What are the three ways in which we can do the inference? Inference is that we can use it. One is the web interface, like how you're using ChatGPT and others, right? That's the API. OpenAI also gives you API, right? So you can programmatically access, you can send a prompt and you can get a response back through an API. It's like you send up few packets and you receive few packets over internet. Okay. Or you can, what I was showing you, you can install on your local server or your desktop and you can play around with it. All the three things works. In case of closed source, only the web interface and API will work. Obviously you will not. The third version is only true when it is open source, right? You can download the weights and the parameters. We already talked about training versus inference. So training is you can imagine that it's a more involved process. It's a more heavy process, right? And it takes 12 days and 6,000 GPUs. And that was also a few years back. Now data would be, you can multiply it by 100 times or something. But let's double click on the generative modeling part, right? So because that's the whole essence of how this 10 terabyte of data got compressed into 14 GB worth of floating numbers, right? Let's see it in one dimensional. So on the x-axis over here is the pitch. The pitch is the quality of the voice, which determines the shrillness or sharpness of the voice. Okay, so I have sampled some male masculine represented by green and the pink represented by the feminine. So feminine voice has higher pitch, right? And it's towards the right. And the probability, this is called probability distribution. The probability distribution represents nothing but when I have sampled and I have trying to draw a curve out of that, is that how likely a voice is, and this is completely based on the samples which I have collected, and then I have drawn the distribution, that how likely a voice is coming from the male and how likely it is from the female. So we have two probability distributions, and this is again coming back directly from the samples, and let's assume that they are, by chance, that they are normal curves, Gaussian curves and all those things, right? With that being said, if I have a normal sample, if I have a new test data, right, a new pitch sample, if it falls over here, I can always say that, okay, there is a higher probability that this pitch belongs to a man than a woman, right? Because there is a higher probability assigned to a man at this level than a woman, right? Now let's break it down in our case, that what is distribution. During the training time, a large language model is nothing but they are constructing these distributions, right? Okay. And at the test time or the inference time, we are sampling from this distribution, right? So I hope you got the idea between what is the distribution and how we are sampling the distribution, right? So this is in one dimensional, which is very easy, but expand that to two dimensional and the things start looking this, and beyond this probably our human minds can't even comprehend. But these large language models, they operate in like multi-dimensionals, more than 1,000-dimensional space, right? And they still do the distribution. They still, during the training stage, they make the distribution and then they sample it during the runtime or the test time. Okay. Hope that gives you a little more clarity on what this generative modeling is all about. Okay. Open source, closed source, we already talked. This is the, by now Meta has already released the 3.1 version. But if you see the way it is read is that this is released from Meta, this is Llama series, this is 3.1 version, and this is 8 billion parameters. One thing, friends, you would notice that there is pre-trained version and fine-tuned version. We'll just go there in a minute, but let's first see what are these. So there are different number of parameters. The rule of thumb says the more the parameters, better the model is. Okay. The other thing is this pre-trained and fine-tuned. In fine-tuned, if you see, there is an instruct word coming after that. That means there are two types of model. One is the pre-trained, which is also called foundational model. So they are just trained on the chunk of data from the internet. Okay. The fine-tuned model, on the other hand, have also been trained. They are pre-trained model, but after that, they have also gone through two mirror steps, or at least one more step, which is called the fine-tuning stage. What they have done? They have done to make that next word or next token prediction, which was coming out of pre-trained, into a helpful assistant, which can ask questions and which can, even when you ask a question, it will give you a genuine response, right? Or human-like response. Let's understand that one more time. Pre-trained models, which Meta has released, or every company does that, is the first step of the process. In that step, it is nothing doing. It is as simple as predicting the next token based on its training, based on its pre-training. Okay, it was trained on a large corpus of data from internet, and it is doing is it is predicting the next token. So if you ask a question, it will respond you with a question, not with an answer. But that was not very helpful, right? If you ask a question, we want an answer for that. That stage comes into fine-tuning. So once the pre-training stage is done, it is fine-tuned with more data which are in the shape of question answer. So the model learns that oh, okay, I do not just need to spit out the next token which comes, but I need to spit out in such a way that it looks like an answer. Okay, makes sense? So how it was trained? We have already seen that how it was trained, right? And this is probably like a couple of years back. Let's break it down. So how many GPUs, and this is the pre-training stage, the first which spits out the next token or the next word, right? So 6,000 GPUs trained for 12 days. The fine tuning is more involved and it doesn't need so much of data, right? So if you see, instead of 10 terabyte of data, we are only training it 100K, but the quality matters over here. These 100K are curated by humans, a proper question and a proper answer for that, and that has been fed, right? If you see on the left side, this user and the assistant, so the model has been fed on 100K question and answers, right? So that the model learns that next time if somebody asks me a question, I need to respond not with another question but with an answer, right? And since this is only getting trained on 100K, this process is relatively faster to achieve. This is a more time taking, and hence with GPU the cost also goes high. So this is more costly, time taking process, while the fine tuning stage is a relatively cheaper, less time taking step, right? There is a third step also, but before that, let's talk about the fine tuning stage, right? So what happens is that after that, what we'll do is that we get the answers during the testing time. When the model researchers are testing this fine-tuned model, they will get the answers, and suppose the answer is not up to the mark, the human system or a human, a contractor, an employee will grade that and correct that and feed it back into the model for the next iteration. So the model will know that, oh, okay, I spit out a bad response, my owners didn't like it, and they want me the response in this format. So that is the learning part, and that happens very, very iteratively, right? Okay, there is a third step also, which is called reinforcement learning from human feedback. Okay, what is that third step? The third step is the first step is unlabeled data. This is also in the space of self-supervised learning. This is more supervised learning, where what we are doing is we are sending 100K worth of prompts and responses, right? This third is that when a system is during the testing, it generate multiple text, right? Multiple responses. The reinforcement learning works on the principle of very much like how a young child is being taught by their parents, right? If the child does a good work, he is given a candy. If he does a bad work, he has been scolded, right? So reinforcement learning also works in the similar way, that it is based on the awards and the penalties, right? Rewards and the penalties. So if the model gives a better response, a good response, it has been rewarded. So the model knows that I have to generate more such responses, and whenever it generates the bad response, right, it has been given a penalty that don't generate that, like you can imagine the hateful or toxic comments, right? If it starts generating, then it has been given penalty, so that in the next iteration models should not generate such responses, and that is done with a very human interaction. That's why they are calling it the human feedback. Okay, so 3-step process for getting not a foundational model. You can get a foundational model right over here, but to get a chat GPT like model, which is called assistant or instruct model, you need to complete all 3 steps. The last 2 steps is called alignment. The first is that when it has the knowledge of internet and it can predict the next token. That's the first step. The next 2 step is aligning it towards the question answers. Okay, it is this is about the third step, right? So if somebody asks you to write a haiku or Japanese poem about paper clips, and you ask multiple times, for a human or a human labeler, it is much easier, rather than generating or writing a haiku, it is much easier for us to select which is better or not. So we are much better in grading from 3 options than generating those 3 options. So in reinforcement learning, what we are doing is we are just grading it, like we are giving that this is a good poem, this is not a good poem, right? So and feeding it back to the model, so the model gets the response that, okay, I need to generate more like this and less like that. Okay, you'd imagine that in step 2 and 3 are more human intensive. So that does mean that there are a lot of humans which are working for that? Yes and no. Yes is that more and more powerful these large language models start becoming, there is more data which is getting generated from the machine itself for the training the machine, right? Okay, so think it like this. Maybe in GPT 1 or 2, there were more human involvement, but once it starts progressing, now the machines or the previous version of machines or the GPTs are becoming so powerful that they can also generate good user prompts, right? So the humans, rather than writing all the user prompts and responses, they would be more checking or grading them that okay, these responses are that, let me pick 5,000 out of that, right? Because the job has becoming much easier for the human. So it is increasingly, these trainings are shifting towards machines. Okay, so that's at a high level how the LLM works. Now let's go inside how actually an LLM functions. If you recall our Venn diagrams, then your large language model is nothing but it is fitting inside deep learning. Deep learning is nothing but artificial neural network, and we have to understand how artificial neural networks works. So artificial neural network works on the simple principle how our brain neuron works, which is again, if we have to take a very simple pedestrian example, we can take of the perceptron. Think of perceptron, and this may be if you have a background in deep learning, this may looks very easy for you, but somebody who is coming for the first time, I'm just doing this talk for that person. Okay, so please bear with me. If there, let's say, to understand a perceptron, it's a very simple AND gate or a decision making machine, right? There are two variables, x1 and x2, and let's name them. So let's say this machine takes a decision of whether you should go to the movie or not. Okay, the x1, and there are two variables which will decide whether you will go to the movie or not, right? The first one is a taxi, whether the transport is available, and the x2 is how is the weather, sunny or rainy. Okay, what we are doing is we are multiplying that by weight. Now weight is something that how much weightage you are giving to transport being available, vice versa, weather being nice, right? What is the, for some people transport is a bigger deal than weather, so the weights of w1 will be higher, thinking intuitively, right? So if you see at the equation, right, if I have to go for a movie, this overall thing should give me a positive value, I'll go for a movie. If the overall things result in a negative value, I will not go for a movie. Okay, so let's see that mathematically can it work, right? So I'm saying that if the x1 is a binary choice 1 or 0, and I'm multiplying it by w1 some weight depending on whether the transport is present or not, it could be 2 3 4 5 some number. Similarly, I've assigned a random weight for w2 and multiplied by that. And then I'm summing these two things up. So I'm summing these two things up. And then I'm subtracting a threshold. So if that crosses a threshold and that number becomes a positive number, I will go for a movie. If that numbers become a negative number. Now, during training, if we have lot of samples or past historical data that whether the transport is present, whether it was sunny or not, can we not train this to arrive at the, to know the weight of W1 and W2, that what are those weights, W1, W2 and B. These are the parameters. When we are talking about the 7 billion parameters, these are the parameters. These weights and biases are nothing but we are referring as parameters over there, right? So all it is doing during the model training time, like when we are feeding a lot of data into it, it is trying to ascertain W1, W2 and B so that my prediction matches with what was there on the ground truth, right? So if let's say for example this thing was a positive number in one of the samples and this was w1 and a particular value of x1 and x2, and I will try to assess w1, w2 and b in such a way that more often than not my y which I am predicting matches with the ground truth what was there in the sample, right, or the training data. This is the crux of perceptron. I do not want to go into detail, but you expand that and you arrive at a neural network, right? Deep neural network. Why? There are many layers of that, but this is nothing but a perceptron, a more complex perceptron, right? Quickly going how LLMs are trained, there are two things to let's say we feed the data, and LLMs are nothing but, at least in the pre-training stage, they are spitting out the next tokens, right? How they are spitting out the next token? Suppose we feed them cat sat on a dash and we have to predict the next word. The next word would be mad. Let's say there are 20,000 words in English dictionary. Any word can come cat sat on a dash. On that dash position, any word can come, right? But the way we have trained this model, that the mat has the highest probability of coming after this particular sequence of word, and that's why we'll put mat over there. And we will put, after that, what we'll do is we'll put cat sat on a mat, and then again we'll join append mat, and we'll ask is to predict the next token. The next token may be a comma or a full stop depending on what the sentence, and then we'll append that comma or full stop, and then again we'll ask the next question. But it may come but, it may come rat, or depending on how it was trained, what distribution it is seeing from the internet, it will start predicting the next token. But the next token will always be predicted based on what? Based on the probability of the next word from the corpus of English vocabulary, right? So few things. One is the vocabulary, we'll deal with that. The next word is this prediction word, and the third thing is that how many such words in past it sees, right? So let's break it down one by one. Tokens is nothing but, you can assume it is a word, but actually it is a subword, right? So scientists and researchers have found that words is not the right length to pass it on, but subword. Let's say, for example, lovingly, seemingly, they all have ly. Seem and love is the root word, right, for that. So does it make sense to use love and seem as that, or lovingly, seemingly as a separate word? Like, that's the whole idea of tokens, so the subwords. Context length, that how many words you take into the chain, append the next and predict the next word, right? And then again append and then predict the next one. Then again append into the whole sequence and predict the next token or the next word, right? That is the context length. Context length is a very big deal, because think it like that. That's like the memory of that. Like, you have the number of computations over here will start growing enormously if your context length starts becoming bigger and bigger. Okay, and at the end, what you are doing is you have the vocabulary, the whole vocabulary, right? Maybe it is 20,000, 50,000 words or tokens, right? But you have to do a prediction for the next token on all the 50,000 words, right? And whatever is the highest one, you pick that, you append it into the context, and then you start the process one more time. Okay, I hope that makes sense. At a 10,000 feet level, this is how LLM works. But there is a problem, that can a neural network understand words? Unfortunately, no, it only understands numbers. Computers understands binary digits, neural networks understand numbers, floating point numbers, right? So you have to supply them into the numbers, right? What is the way to convert a text into a number? There are several ways. One easy way we could have done was that what is called one-hot encoding, which is like every word will, like, let's say we have a vocabulary or a dictionary is 20,000, so we can make a 20,000 column matrix, right? And for each word we'll only put one place for that word, like add work, the first place should be only one, rest all zeros. The black should be like, the second place should be one, rest all zeros. That way we are quantizing or the whole of the vocabulary, a whole of the words into a separate binary 1-0 matrices, right? 1-0 based matrices. But is that this results in a very sparse matrices and other problems also creep in. So what we do is that we make them into a concise vector, right? Concise vector, okay? Now, what is this concise vector? Just to give you, and this is the essence of embedding. So when it comes embedding, over here, if you see the black and the cat, if somebody has to make sense out of, the computers have to make, or models have to make sense out of black, there is no difference between black, cat and duet and zombie, because all has that one bit as positive, like that one place as 1, rest all as 0. But obviously there is a resemblance between cat and, let's say, feline, or cat and dog, than cat and water, right? There has to be some relation. So the let's say a man, let's say in this particular example, right? A boy, a child, an infant and girl, they are all similar nature. But if we start representing it in this way, there is no inherent meaning coming out, right? So scientists thought that, okay, maybe there is another way of representing, and the way they represent this in a more concise way is let's say this is a 2D example, okay, and we only have two vectors, okay, or two dimensions. So one is represented as gender and the other is age. So anything which is towards the lower half where the y-axis is low or the age is low are boy, child, infant and girl. So they are all closely packed together each other. You see the child and infant, they are gender agnostic and they are together. Boy is towards the left. So anything towards the left, if you see, they are masculine. Anything towards the right, they are feminine. Okay. This is how computers or models understand words, right? They're not understanding words just by plain vanilla one hot encoding, but by this. And this is called embedding. Why it is embedding? Now you can represent these words or text into these coordinates, right? You can represent these coordinates. And when we have to make sense out of these coordinates, we know that this coordinate and this coordinate, child and infant, they are very close together. Maybe they are synonymous or they have some relation. So it brings out the semantic relationship between words, right? And that's what the embedding is. But when we do embedding in real life, these columns which we are being shown over here, they are not, we cannot decipher, we cannot make sense out of it that they are represent age or gender or any other characteristic or property. They are at a much more abstract level, but nonetheless it results into a dense vector, okay, where the semantic relationship between two words are preserved. The two words on this multi-dimensional vector space, two words, if they are like let's say man and person, they will be very close together than man and table, right? So their closeness in that vector space, which is preserved, right? And that's the essence of embedding. Okay. What was vocabulary? Vocabulary is the entire number of tokens on which the large language model is trained. So this is, treat it like dictionary, right? And here I have taken some examples of it, right? If you see that foundational model, when I try to run it, it is just spitting out the next token, and next token is not very helpful, right? It is saying what is the capital of India, New Delhi, what is the capital of New Delhi, and it has not been fine-tuned. It has not been very useful. Now you'll ask that if it is not useful, why it is being trained also? But that's the first step where you have to go through, where it understands the internet, understands human languages. And in case of open source, companies like Meta has given to you so that you can fine tune based on your need. Let's say you have you work in a medical industry or a banking industry, you can fine tune the model based on your data, your corpus of data, where from the pre-training stage, it retains the nature or the nature of human interaction, human words and human languages, and you train it on a specific knowledge which belongs to your enterprise or your group or your organization, right? That's the reason. Okay. Another thing is that why these embeddings and contexts are very important, because a same word in English can have different meaning in different contexts, right? The river bank got flooded. Let's say the example was the river bank got flooded. The bank over here represents river bank. The bank does not represent the physical banks where people keep money. Similarly, the examples, I went into a dark cave and suddenly I saw a bat flying overhead. This bat is an animal, while over here he swung the bat. This bat is a cricket bat. The third scenario is that she tried to bat the mosquito. She tried to kill the mosquito. So context is very important. That's the reason that when I was saying that it has to retain a long context to make coherent sentences, that's the meaning of context, right? If the context is like just two tokens, there is no way. That means we are only supplying saw a bat. With this, it cannot generate the next token. It will not know that this saw a bat, whether we are talking about a cricket bat or we are talking about an animal. But when we see, I went into a dark cave, and suddenly I saw, with all those context, previous tokens, the large language model have the ability to make sense out of it, right? And that's why context length is important. Okay. So here is few of the things like, what is the context length? We are talking about context length. It's roughly 4,000 tokens, right? It has like few of the latest models which are closed source have like 32,000 right? 32,000 tokens, that means 50-70 pages worth of data. And you can push and you can ask for the next token prediction and it will do that, right? Okay, this is also over there. How the performance metrics are derived. So there are various performance metrics measures which had been done. So based on coding skills or common sense, and these all various companies have, or various organizations have put together a sort of a performance question answers, right? And various models are getting trained on that, right? So on the math skill, reading comprehension, world knowledge. So the various companies go through these testing to popularize their model, that my model stands on, like, now it can solve maths olympiad, it can solve SATs also. So there are various such performance metrics also available from various organizations. How it all started? It all started with a paper in 2017. The paper is called Attention is All You Need, and it proposed a transformer architecture. Now, I do not want to go into detail because this is a very high level, but you should understand that when I was giving you the example of context, that bat over here, this bat is an animal, can only be figured out by model because a dark cave is present, right? Otherwise, there is no way of us knowing that this bat is an animal, or this bat and this flying. So obviously this cricket bat cannot fly, right? So this bat and flying, like, because of these words like flying and dark cave and all, we can make sense out of it. Transformer is exactly doing the same thing. What it is first doing, it is tokenizing. So it is bringing into a smaller chunks. After that, it is doing embedding. That means that words are getting transferred into floating point numbers. And after that, it is passing through a deep neural network. In that deep neural network, the magic happens. And the magic is that it is putting its emphasis. It is trying to put attention onto those words through which it can gather the meaning, right? And that's how it is getting trained after that. Okay, so there are various models like that, but essentially it is doing a net worth prediction. It's a blue sundress, it's a blue, and then you have the probability distribution, which I showed cat sat on a mat. Again, a probability distribution. From there it picks the next token based on the highest probability, and then again it appends and it start predicting the next token. Okay, so this is more elaborate way of doing that. If you see that these are the vocabulary IDs, that why vocabulary IDs? Because you have to retain that which word corresponds to which ID, right? Because your token has to be assigned a physical ID so that the mapping back can happen. Because if the large language model spits out a bunch of vector numbers, it will not make sense to us, right? It needs to be converted back into human readable format or decoded, so that we can make sense out of it. Okay. Leaderboard, there are various, on Hugging Face there is a leaderboard where what they do is that they sort out by rank that which GPT or which large language model is performing how much, right? So most of the closed source models will be on the top because they have been trained off large data for a large time frame, right? But you see Llama and all are also in the top 10 or top 15 over here, right? So you can always play around with the open source model also. What is the future direction which is happening? One direction is that there is no limit right now. That bigger the GPU clusters, bigger the corpus of data, better the model will be. It is not tapering off, right? So there is, without any algorithmic improvements, like transformers came in 2017, but after that, we are only adding bigger and bigger transformer models, right? Without having a new algorithm altogether. And we are training it on a bigger and bigger GPUs, consuming tons of energy. And we are training it on a larger data set. And we are making the model bigger and bigger. Like earlier it used to be 7 billion, 20 billion, 30 billion. Now we are hearing about 400, 500 billion parameters. Parameters are nothing but weights and biases, right? So that's the direction in which it's doing. It is the wave is not tapering off. Okay. The other thing which has happened, which is kind of nice, is that earlier for all the different deep learning tasks like computer vision, speech, translation, reinforcement learning, all are getting together with transformer, right? So that's the single architecture which is propelling all these. They used to have separate architecture for themselves for the different use cases, but now everything is coming towards merging towards transformer. Okay, The, the next two slides are dealing with that where the world is moving on. The first is the retrieval augmented generation architecture. You may have heard about it. Suppose that large language model also need to tell you about something which is just proprietary, which is just knowledge to you. Like within your organization, there is some knowledge base article and it has to get sense out of that also. Can it do that? Because that was not the training data which was given. Suppose that you ask the question that, okay, what was the like, let's say it's a sales database and you have to query that sales database and get the answer for that. That information will not be readily available on a public site, right? That's proprietary to your organization. But if suppose you want to make sense out of or you want to gather that information, what you do is that LLM understands the general knowledge logic, right? It can write code also. So what you do is that you augment your proprietary data into the prompt and then ask LLM to make sense out of it, right? So you store your proprietary data in something which is called vector database, right? And then when you ask the question, you first send the question back to your vector database based on similarity search, that how common, this is more like Google page ranking, like how common that particular chunk from the vector database is relevant to your particular question. It gathers that, it sends, and then it combines both the things, your prompt and the gathered information from your proprietary database, and sends it to the large language model. Large language model processes that in a human readable format and gives the output, right? The second is agentic AI. Again, this is a one step above that RAG thing. Here we are talking about agents and tools, right? What are agents? What are tools? Agents is something like tools are something like these are hooks, or these are suppose you have to book a ticket, or you have to go to internet and search something, or you have to know the latest price of a particular stock, right? Will LLM models be aware of that? Because the models have been trained like 6 months down the line. It doesn't have any information on what is going ahead in the world today. That only can be given through, let's say, Yahoo Finance or these stock type websites, right? So what you can create is that you can augment your LLM with tools and agents. What agents do is that when you send the prompt, the agents break down that prompt into sub tasks. Each task, let's say, is assigned to a tool. Suppose the task is, let's say, for example sake, the task is that, okay, what is the current stock price of Tesla and how it will grow in next 5 years, right? For that, what you need to gather the stock price. So you need to have a tool. So what agent will break it down into tasks, right? The first task is, okay, I will send it to first tool, let it grab the stock price, and then what I will do is I will see how Tesla prices are flowing. I'll extrapolate it and then give you the 5 months projection, right? So I can use calculator, or yeah, you can use Google search. So the various tools or hooks are present, right? And the agent is one who is breaking down into the subtask, right? And finally, it is fed to LLM so that the LLM can massage this whole thing and give you in a very, very concise, human readable format. So that's another thing which we have to keep in mind, which is going. Okay, with that, it brings us to the end. These are my coordinates. If you want to connect with me, please feel free to do that. I also take data science, both classroom and online data science, machine learning, generative AI courses. If you are interested in any of those courses, do ping me over here on whichever platform you see this. Okay, I'll respond to you. Thank you. Bye.